our speaker for today is Professor Li from China. Xing Zhong Li is his full name. I first met him in Italy at the second conference on cold fusion held in Italy in 1991. And I've also seen him since then at several other conferences. And in fact, the conference in 1996 is being planned for China in the planning stages. It'll be a conference, and Professor Li will be in charge of that conference. But that's a couple years away. The next conference in this area on the subject will be in France in March of next year. So this is quite a controversial area, and as everybody knows, but it'll be interesting to see what's going on in the country of China in this field. Professor Li has spent 6 years in the United States, so he knows our customs and so on pretty well, speaks the language quite well. He got a PhD degree in theoretical nuclear physics at Tsinghua University in China, then also got a PhD in plasma physics at the University of Wisconsin in 1983. Then he also spent 2 years at the Plasma Fusion Center at MIT, so he has a lot of expertise in both hot fusion and cold fusion. In fact, in China, he's on the Fusion Research Advisory Board for the country of China. And so he's given talks on both hot fusion and cold fusion. He's on a kind of extended tour. He visited SRI, which has the biggest cold fusion program in the United States, about $1.2 million a year at SRI. Then he visited BYU and Steve Jones that has some research going on. And Los Alamos has a group of about 5 or 6 people. He was at Los Alamos last week, and after leaving here, we'll go to San Diego where several people are working in this area also. The reason we're videotaping this is my sponsor, Bob Nowak, and several other people at other Navy laboratories would like to see this seminar, but this is the only Navy laboratory that he's going to visit, so we're also videotaping this today. So I'd like to turn the time now over to Professor Li.
Thanks, Dr. Melvin, for your introduction. My talk will be searching for truth with high expectations. Everyone knows this research started 5 years ago, and after the Santa Fe conference, it became quite quickly. At that time, we had a national conference in China, and we discussed this, and we said if only 1% of these are truths, then it's worthwhile to invest, to dedicate yourself in it and make it into 100%. That's why we mean that searching for truth with high expectations. It's particularly important for China because we cannot afford the hot fusion. The cold fusion is not the best terminology as we understand now. What we say is put the palladium and the deuterium together, then we will see a lot of heat out more than the heat in. If you explain this by the DD fusion, it's abnormal because it's too cold. And more than this, if we look at this reaction, why there is no neutron, and we look at the radiation, it's smaller than we expected. Particularly, it's not easy to reproduce. So all this make it very difficult to explain, to understand, and someone say this is even not true. But we don't believe this, but we have to explain why we have such amount of energy, 1 watt. If we continue for more than 1 month, it's about the energy of 1 megajoule. This is the energy from a grenade. Why so much energy coming from this system, and who is giving this energy, who is carrying this energy? We don't know. That's why we are searching. But it's very important for energy research and for fundamental physics. It will have big impact on these. That's our high expectations. I try to start from the general system in China for this kind of research. This is the highest level, the state council, like your Department of State. Under this, we have the commissions for education, state commission for science and technology. And we have a lot of ministry for the oil, coal, nuclear industry like this. Usually, these commissions is higher than the ministry because the head of this commission usually are the vice premier of the state council. And this state commission of science technology is supposed to be responsible for all these researches. You can see the Academy of Science, the Institute of Chemistry, Institute of Physics, Institute for Applied Chemistry, and Institute of High Energy Physics. They are all engaged in cold fusion. Particularly, the Institute of High Energy Physics, usually the physicists in high energy physics area will be against the cold fusion, but some of them are very active. At the beginning, they saw some radiation from the discharge system, but they didn't see the neutron, so they gave up. They say, oh, this radiation may be noise. Later, the whole world say this abnormally involves energy without neutron. Then they go back to their experiment again. They say, oh, we saw this radiation with no neutron, so that's true. So they start again, and recently they obtained some result. They try to identify the peaks in the radiation, and Professor Hagelstein at MIT is interested in one of their peaks in the Maui conference. So they are excited and continue this work. So this is a Natural Science Foundation, which is responsible for basic research, but they have no institute under it. Usually we submit the proposal to this foundation, and they send to the reviews, and the reviews come back with a grade. 5 reviews with more than 3 grade A, then you get the support. But usually cold fusion cannot obtain 3A. So it's very difficult to get the support. Fortunately, the leader of Division of Physics 2 was responsible for the cold fusion research. And he has special fund under his own control, need not the grade A. Then he said, if someday cold fusion is proved to be true, then he will be very embarrassed. So he said, I would rather put this money on the cold fusion. Of course, he takes a risk because a lot of criticize from the senior academician. But anyway, we obtained a small amount of support from the Natural Science Foundation. This is the most research money. We call it the High Technology Program. It started in 1986. 4 senior academicians wrote a letter to the highest level and said, if China wants to be survived in the next century, we have to invest money in this important research. Then fusion was one of this item. We have a total 100 items under this program with about 10 billion in 15 years, 100 subjects, and fusion was one of them. And this hot fusion, about 20 million a year right now. That's Chinese dollar. I'm serving this advisory board, but at the same time I'm working on the cold fusion. That's different from the situation in other part of the country. And under this commission, there is another division called the Fundamental Research Division, which is supposed to be responsible for all this fundamental research. They put up a program called the Climb Up program. It's for basic research. Then it is confirmed has a good future. Right now, cold fusion research as a candidate for this program. We obtain a little money, about 150K every year. And I can make a recommendation for the distribution of this money, but I do not control this money. I hope if we work hard, then we will become the climate program. Then if next year in France, freshman ponds give a demonstration of their experiment and the whole world become more convincible, then we may push up this into this program. Then we will have more research money. And these are other systems. At the beginning, 1989, everyone wants to have their own team for the cold fusion research. We thought maybe this is another kind of breakthrough like the high temperature superconducting material. But later, a lot of institutes dropped, but these are still there. The Institute of Atomic Energy, the Southwest Institute of Physics, this is the Hot Fusion Institute. And the Sichuan Institute of Material and Technology, Southwest Institute of Nuclear Physics and Chemistry, and Institute of Applied Physics and Computational Mathematics. I think some of you may know this. These are all universities under this Commission of Education. Some university dropped, some university goes up. And in the total, we have about 17 institutes in China.
17 working on cold fusion.
Yeah. This is just a distribution geometrically. Everyone knows this is Yangtze River, this is Yellow River, and most of cold fusion research concentrated in Beijing, about 8. That's the Sichuan fluid. This area we have about 4 institutes. The total 17, 12 is there. And the whole country general attitude is a kind of good, I think, because in 1991 we have a National Congress on Nuclear Physics Society, and the executive member of the society invited me to give a talk about cold fusion after the Como conference. And I talk about the Fritz-Wells tritium experiment there. And I try to keep the low key in this 300 people audience. But after my talk, they come to me, they say, you should speak louder. And they say, we did something and we were forced to stop. So we try to give our experience to you. They sent me the print and their experience to me. In 1992, after the Naval conference, I was invited to give a talk there. That's an inertial fusion conference in my country. And in 1993, I was invited to give a talk. That's a plasma physics conference. So general attitude is good for cold fusion research. At least we are not considered as a pathological science. So in 1993, I attended a Maui conference. This year there will be in Russia, the Belarus. Next year will be France. And hopefully, 1996, I will welcome you to visit the Great Wall in Beijing. After the general situation, I try to talk about something about experiments and something about the theory. In the experiment, we concentrate on 2 items. First is the Chinese-based reproducible experiment. In order to study it, we have to have some experiment. It's based in China, not just to say, oh, some scientists in the world, they reproduced. It's not easy for us to study. But later we found that in order to do this kind of Chinese-based experiment, the gas loading experiment, the electrical discharge experiment, excess heat with titanium rod, we need to study some key parameters. We just drop this detection for the charged particle for radiation for excess heat. Just concentrate on the key parameters as a precursor. If we put everything together, it's difficult to study. We just study the precursor, the loading ratio. So we spend a lot of time on this. So today I'm going to talk about this and talk about this. For the theory, we always ask us the question, who is the energy carrier? If 1 watt excess heat, if the carrier carries 10 MeV for each reaction, then you have more than 10 to the 12 particles per second. This is well above the sensitivity of modern technique. We have to see them. If we don't see them, maybe another mechanism. The second is we ask the question for the closed system. If they emitted energy, 1 day by 1 day, 1 month by 1 month, the energy leaving, then the closed system should go to the lower energy state. Usually the material we are using is less than 1 mole, and after 1 month, 1 megajoule were emitted. Then if every particle goes down in their energy state, they will go down by about keV. Then who is this? We ask the question, after 1 month, if something drops their energy, then they may go back sometime. So this time when I visited Stanford University, I asked them, you are using closed system, whether you have seen any negative heat, not excess heat, because this one may go back sometime. You should watch this negative heat. The second question. The third question is the penetration of Coulomb barrier. If there is any nuclear reaction involved, there must be a problem for the penetration of Coulomb barrier. So if there is a kind of penetration for the fusion, we may ask a question whether there is any influence on spontaneous fission, because spontaneous fission is caused by the penetration of Coulomb barrier also, but from inside to outside. So we try to study an experiment in China using the uranium-238, and which is a good absorber of hydrogen. We will investigate what's the effect on the spontaneous fission. The second is, if any negative charge to screen the Coulomb barrier, maybe the electron. Even though we do not understand what's the mechanism, we may try to find the high density region for the electron. And the positron is very good to identify the high density electron region. So we try to use the positron annihilation technique to verify this idea. The third is the electrolysis of pressured heavy water. Freshman ponds stopped their experiment due to the boiling. That's 100 degrees. And we have the technique in pressure water fission reactor. This institute is interested in doing this experiment. They say we just put more pressure on the heavy water and do the electrolysis, then the temperature will increase, then we may have greater excess heat. It's easy to measure. So this is just after assembly we started the experiment recently. So that's the general situation. Now I go back to this one and this one. The gas loading experiment is different from the that in the world. The Dr. Naval and Scaramucci in Italy and Jones, they did some gas loading experiment at the beginning, but they tried to detect the neutron. At that time we proposed, if there is any abnormal nuclear reaction, neutron is not the necessary product. The energetic charge particle is a necessary product, because two charged particles collide each other. Must be one of them is charged, but not necessary to be neutron. So we start to detect the detection of charged particle. Because using the gas loading technique, it's easier to detect this. If we use electrolysis, it's more difficult. We did some experiment along this line. We found some charged particle, but it's not a very good reproducibility. Then we start this study. So I will talk about this. This is the first picture we reported in the Como conference. That's 1990. We use CR39. It's a plastic charged particle track detector to detect the charged particle. Here is a sample. That's a piece of plastics. If we put this plastic with a palladium sheet and we load the palladium sheet with the deuterium or hydrogen, then we will test is there any energetic charged particle from the surface. When the charged particle penetrates these plastics, it will create a damage. Then we put this in the chemicals. The etching process will create a pit along this damage. Then we will see this kind of image. When the particle inject vertically to these plastics, create a circle. If they inject along an angle, then create a shape like a sesame seed. We count this number, we know how much radiation from this surface. So that's the first result. And later we try to reproduce them. In 1991, we used the same batch of palladium sheet from Russia. The density of here is about 10 to the 4th per square centimeter. But if we use this palladium second time, the density is much small. Because this was imported in 1960s from Russia. We used all of them. Then we switched to the palladium from the United States. The density is lower than this one. Then we start to use palladium, titanium. It's an alloy with vanadium, aluminum, and tin. The density is almost same, about 10 to the 3rd per square centimeter. The background usually is less than 100 per square centimeter, even 10 per square centimeter. We monitor this every time.
How far is this film away from the electrodes?
Thank you. This is a picture of this experiment. In fact, this is not electrolysis. We do not have electrode. We just put a piece of palladium sheet in the center and use the CR39 and a piece of TLD, that's thermoluminescent detector. Put them together like a sandwich and put this in a brass container, or sometimes we use stainless steel container. And this container will connect to a pump or a gas bottle. Usually we put in the deuterium gas about 9 atmosphere and cooled down by the liquid nitrogen duo. Then we seal it. When the liquid nitrogen evaporates, the temperature goes up. Then we just do this cycle, high temperature, low temperature cycle. After this, we take them out and watch the image on the CR39. In the same time, we watch this TLD because we believe some precursor. During this process, the electron will change its state. Then they will emit some electromagnetic radiation. And the TLD is supposed to sensitive to this kind of radiation. And take them out and heat it and monitor the visible light they emitted. The amount of visible light they emitted is proportional to the radiation they received in the container. So this is the result we obtained. These three columns is for deuterium cell. It was filled by deuterium. This column is for the hydrogen cell. We filled with hydrogen instead of deuterium. And this is a blank vessel. You put nothing, just put this TLD and Cl39 in it. And this is a lab background. We do not put in this vessel. We just put on the wall, the shelf, monitor their number. For the first one, the deuterium cell, we have two. We obtain this TLD number 100 about 200. In this hydrogen cell, we obtain 158. The next one, we didn't put this and put this too. We can see in the deuterium cell, the reading is usually higher than the blanket and the background. This third one, fourth one, and in the fifth one we have this deuterium, hydrogen, and both.
So hydrogen is almost the same as deuterium.
Yeah. This fit with our theory because we believe the hydrogen or deuterium get into the crystal, and during this temperature cycle they will change their state and emit some electron radiation. But some of this state will help the deuteron interact each other, then create charged particle. So if we take out this, we have the TLD signal from both hydrogen or deuterium. But for the Cl39, we have signal only with the deuterium. This means in the hydrogen system, Cl39 didn't see any image. So this means they change the state, that's same, but the interaction only happened for the deuteron. But the problem is this kind of experiment reproducibility is not very good after we used up all the Russian palladium. Go to the new palladium, the intensity of the charged particle reduced 10 to the third. When I asked the expert from UC Berkeley, the Professor Price, he said that usually it's easy to obtain a contamination from the radon in the air. So if you have this kind of signal, it's very similar to alpha particle. So if your intensity is less than 10 to the third, it's not convincible. He suggests me to produce more like the first picture. If we can obtain something like this and frequently reproducible, then it's worthwhile to study further of this. So we just switch off our experiment to the loading ratio, because we believe the loading ratio is very important for this kind of reproducibility. I learned this from the Stanford Research Institute. This is the loading ratio, how much deuterium for each palladium. This is the resistance compared to the R sub 0 is the palladium without deuterium loading. So the resistance will increase, then drops. The peak is about 0.72. So we start to learn how to load this deuterium sheet, and we found it's very difficult to reach other side of the peak. It's easy to do in this side. So this explains why in 1989 a lot of labs failed to reproduce this experiment without monitoring this loading ratio. So Stanford Research Institute told me it's important to make them higher than 0.8, and we couldn't go this region very easy. So then we started the research. They are doing the electrolysis, but we started the gas loading experiment, try to load the palladium to the other side of this peak. But if we look at the phase diagram, that's for hydrogen. This is the pressure This is the loading ratio. This is the curve with constant temperature. If at 30 degrees C, if we reach 10-day atmosphere, this number is much less than 0.8. So we didn't believe we can do this at a low temperature, room temperature with the pressure we can reach. You see, this is the number from this kind of phase diagram. 1 atmosphere, 25 degree, the equilibrium number is 0.69. That's not good for cold fusion research. We need this number much greater than 0.8. So we just try after the Como conference, because Fritz Will said if you use multiple step loading, you may cross this peak. But he didn't reveal the detail in his electrolysis experiment. He said just reproduce, load once, then deload, then load, may cross this peak. Then we try in the gas loading experiment. We tried a lot of versions. This is a recent version. This yellow part is a stainless steel container with ceramic support, and this red one is a palladium wire, and it's sealed. We can pump it and put deuterium gas in. We try to use this system to study 3 kinds of effect. First, we can heat this wire just by large current, see what's the effect. Then we can cool it by liquid nitrogen duo outside, then make the temperature low down. And we can create a kind of discharge between the wire and the stainless steel wall. And at the same time, we can monitor the resistance of this wire to get the number for the loading ratio. The general conclusion is that the heat, the cooling, the discharge has no big effect on this loading ratio. It's unexpected, because in Nagoya conference we expected discharge will have big effect on this kind of anomaly. And I was a hot fusion person at MIT. They use discharge to clean the wall and obtain the record density confinement time, because discharge will clean the wall. So I guess the discharge will have effect on this loading, but it didn't. Why do we do the cooling? Because we expect the cooling down to the liquid nitrogen temperature. There may be some tunneling to increase the diffusion coefficient and increase the loading ratio, but it didn't appear. The heat, if we use heat, the constant heat doesn't work very well, but finally we found that the pulse heat will change the loading rate. So I will talk about this. Here is the picture for the discharge experiment. We put the palladium wire, the cathode, the stainless steel wall is the anode. The pressure inside is about 0.01 torr. This is the time, about 1 day, and the vertical will show 3 kinds of parameters: the temperature, the resistance, and the pressure. The blue one is the pressure. We drop the pressure to start the discharge, and the temperature increase. Then the resistance will increase due to the temperature. So we try to see what's the effect for the degassing. If we start discharge, the gas will leave. Then we think there will be effect on the loading, there will be effect on the resistance. But it didn't appear. You see, the pressure goes down after the discharge. The resistance does not change very much when the temperature goes back. Then we say that's for degassing. What's the effect on the loading? This way for loading, we delete the gas for the discharge. During this discharge period, the temperature goes up, the resistance goes up. After discharge, we increase the pressure. We try to see what's the effect on the loading. If the loading increases, the resistance will goes up. But the rate is very small. It's about 0.2% every hour, because this is 24 hours.
I know which side of the resistance peak you're working on. How do you know you're not on the right side fast?
Yes, that's a very important question. If we want to answer this question, we have to do some operation. First, we monitor the resistance goes up and goes down. Then we degas. We take away the gas and see the loading ratio goes up and goes down. Then third, finally, when we reach this part, we take out the sample and weight it. Previously, we thought when we take out, the gas will leave very quick, so we have no time to wait. But in fact, it's not so quick. We still have enough time to weight it. And the weight proved that we are on the other side. This is a picture for cooling at the liquid nitrogen temperature. The resistance just stays there for 1 day, no change. This part just goes up because the temperature goes up. So it's not as we expected. When I visited SI this time, they told me, if you want to see the tunneling, you have to put in the liquid helium. This temperature is still too high. Or maybe some professor here knew this already. We are learning in the same time we are working. My student is very clever. He invented this scheme. The pulse heating. This is the current through the palladium wire. 5 seconds for 1 ampere. Very thin wire. Then stop. 50 seconds. About 20 minutes for this. Then we will see a big effect on this loading. This red one is the resistance ratio. This period means pulse heating. After pulse heating, you see the pressure drop, the resistance ratio goes up, the temperature stays same. He did a control, put the same palladium wire in the same vessel, that's R star, but this one has no pulse heating under the same condition. The loading rate is much smaller. As a comparison, after the pulse heating, we obtained the rate is 4.5% every hour, but this one is 0.3% per hour. So this effect seems very good for increasing the loading rate, but we later found this one will not reach the point we need. It affects on the loading rate, but will not affect on the terminal loading ratio. This is a summary of the first student's work. He is using hydrogen in 1991 to 1992. We just use the multiple step loading. We put the gas in and degassing and put the gas in, degassing. Using this method, we can cross the peak. And we reached the loading ratio, the maximum is 0.89. We didn't believe this because according to the phase diagram, it's impossible to reach this at 20 atmosphere. So we take them out and weight it by the weighting method. it's verified. This column just shows the treatment is very important. The first sample we treated is annealing method. Then after half a year, we did this experiment. It needed about 16 hours to reach this maximum value. But if we do not anneal it, then we need 75 hours. But if we anneal it 2 days after the annealing, then it's very quick, less than 4.5 hours. 5 days after the annealing is 6 hours. 15 days after annealing, more than 7.5 hours. Of course, that pressure control is not very good, so this is just a kind of a reference showing the annealing will affect the rate. When we use this hydrogen to reach this, then we switch to the deuterium. But he failed in loading the deuterium into the palladium to across this peak. He couldn't, because the pressure is too low. Then he graduated. The next student come, he used the deuterium. That's in 92 to 93. Only one using the annealing, we across the peak and reach the 1.9. So the peak is 2 for the deuterium loading, the curve. The peak, the resistance should be 2, so across the peak, go down again, 1.9. And others, if we use the palladium as it is, the loading rate is low, the maximum value is 1.3. That's not a loading ratio, just a resistance ratio. We hope to reach 2 to across the peak. It's only 1.33 because the pressure is too low. If the pulse heating can increase the loading rate very quick, but the maximum 1.95, it's still not on the other side of peak because the pressure is too low. Then we use discharge. Discharge effect is small. Cooling effect is small. The annealing is most important. If we did experiment after annealing, the loading rate is quick, loading ratio is high, and across the peak, 30 atmosphere after 2 days. And we try to use acid cleaning. Seems it's not very good. After the cleaning, the loading rate is low, and we cannot across the peak with same atmosphere in 2 days. So this is a kind of summary of the experiment we did. And we try to go along this line. We find what's the best way to across the peak, and we can reproduce this loading ratio. Then we will put the CR39 in it and the thermoluminescence detector in it, and we will do the experiment again as 3 years ago. Then we hope we will see more. That's our future plan. Finally, I want to say what's our general impression about this situation of the cold fusion. We think it's very similar to the end of last century. At that time, there is a big argument about what's the nature of the light. It's a wave or it's a photon. Since they are conflict each other. If you say it's a wave, then it should not act like a photon. But if it's a photon, it should have no wave feature, because they are conflict under the classical physics. But finally, they are both okay. We accept them. Maybe the cold fusion in the same stage. Right now, some people say they are excess heat. Some people say if this excess heat, there must be a lot of nuclear products. And some people say we have no nuclear products, then this excess heat is not believable, because it's a kind of conflict But this conflict will be over if we find a good theory to explain both of them. Particularly, Dr. Miles did a very good experiment, in fact showing both of them are correlated. So we hope someday we will solve this problem and we will go to a new stage. Thank you for your listening.
For questions?
Electrolysis. What sort of excess heat levels have been observed by just doing loading without electrolysis?
Yes, that's important, but we do not have good calorimetry with this gas loading experiment. So we didn't monitor the excess heat. In fact, in China, only 3 institutes spend some time on the excess heat experiment. It's very difficult. As you know, only Dr. Miles can do this kind of very fine, important experiment. In China, if we do this kind of experiment, we need a lot of fund. So you see our gas loading, it's very easy and can be done in the university. The only thing is 30 atmosphere always make me very nervous if students work on this. So we have no capacity to do the excess heat.
Yamaguchi in Japan did gas loading and he reported also an excess heat effect in his experiment.
Was it similar to the sorts of things you observed with electrolysis?
About the same order of magnitude, I guess, right? But that's the only one I can remember, right?
Yes. Yes.
He reported helium 4 also in that experiment and also excess heat, right?
Have people tried to use, instead of solid palladium, a very porous palladium where the diffusion distances would be much smaller to load it or to do electrolysis?
I think someone tried this, the Japanese group in the Osaka University, the Arada. They use a special electrode, porous, with porous feature. Yeah, they claim big amount of excess heat.
Has anybody reproduced that?
I don't know. Because Arata himself has no good reproducibility. Yeah.
So at present, the status is that only the heat excess is the one that you say that they may respond, but there is no nuclear products observed so far.
There is nuclear products observed. Yeah, in my mind, the most important thing is Fritz Well's tritium experiment. It's very convincing because his tritium production related with loading ratio. Every time loading ratio higher than 0.85, he observed the tritium production. That's one. And Dr. Miles' experiment showed helium. I count this as a kind of charged particle also. And Yamaguchi, he did this also. Yeah, and he observed the helium also. The charged particle.
And then Los Alamos is reported good evidence for tritium.
Yes.
At Los Alamos.
And the radiation you're talking about must be gamma radiation.
I think so, because it's gamma, but the energy is very low. Yeah, it's about 300 keV or even lower. Recent visit to Los Alamos, they told me that in their discharge experiment, their tritium production is very good. If you count 10 sigma, about 60% to 70% reproducibility. But they obtained some very good result. It's 300 to 400 sigma, about twice in 96 runs. That's a very good result. So these are all charged particle experiment. And I believe the experiment we observed is charged particle also. We stopped just for loading ratio. After we assure the loading ratio, we will go back to this again. Because all this charged particle measurement has to be done in another institute. It will cost us money. So we have to be sure we reproduce this, then we ask them to do it for us again. So there is charged particle, there is excess heat. Sometimes they say they are not quantitatively commeasurable. But I think Dr. Miles' experiment shows their correlation, not very good correlation. Yeah.
The problem is again same as you mentioned here, the Coulomb penetration.
Yes.
That is the main problem now.
Yes.
You know, how they can go so close together, you know. Because you raise the temperature just to overcome that.
Yes.
Barrier, you know. Is there any way that those two neutral atoms, they can fuse into each other and is there any other explanation like that, or what we call screening charge kind of effect?
Yes.
Have a thought on those kind of lines?
Yes. In fact, I'm theoretician. This is the most important question in my mind. I think finally we need a good theory to unify both sides. So if we have a good theory, maybe no confliction at all. And the theory needed screening, and the only candidate, as I see, is the electron. But electron go between two positively charged particles. Based on the conventional quantum mechanics, it's impossible. But recently, someone published a paper about this kind of calculation. They just changed the boundary condition. It's still possible to make the electron shrink in a much smaller radius. At the same time, they will emit the energy. And I try to improve his work. That's something not done yet. But I think I can, because inside the metal, the whole situation different from the two free atoms. There is a good symmetry. This good symmetry will cause the Young-Taylor effect. I think you may familiar with this. Young-Taylor effect just couple the electron with the ion. When we do the calculation, usually we use Born-Oppenheimer approximation, means the electron will separate with the ion. But we need them interact each other. This is only possible in the metal with the Young-Taylor effect. The electron will drop and effect on the ion. Ion will move in and electron will drop. Then this together will create a kind of new state, which may cause the fusion you suggested. This is a dream. I'm working on this.
Would you mind commenting on the politics of cold fusion in China, or is there a lot of opposition? Like there is in the United States, there's a lot of people very opposed to this type of research. I wonder what situation is in China.
I think in China it exists some person against the cold fusion, but we can survive. For example, in the Xi'an, I was invited to give a talk. The chief executive member of Chinese Nuclear Physics Society invited me, but his vice chairman said against cold fusion. But it doesn't prevent from the chief invite me to give a talk. And for the research fund, you see, the senior professor in the academic of science, they against the cold fusion. They just put the grade C, grade B, no grade A. Then we have no fund. But the leader still think that's his responsibility. If someday cold fusion proved to be true, and the Natural Science Foundation didn't support, that's a big mistake. So he still continued the support. And you see, last year in Naval conference, we said discharge may produce the high energy components of neutron. But later we prove it's wrong. We ran 4 electron discharge experiment in China, and we prove it's not high energy neutron, it's an overlap of X-ray. Although we cannot explain why the X-ray is so strong, but it's not high energy neutron. Then we report to the Natural Science Foundation, and the chairman said, don't be surprised. That's usual way for scientific research. As long as you are honest, that's good. That's the way in China.
Any other questions from anybody? We thank Professor Li again for his seminar.
Thank you.